So this link here, bit.ly/netpyneostut, should open a Python Google Colab with some NetPyne code, which runs a simple network that generates oscillations. And we're going to play a bit around with the parameters and see how we can change the different oscillation frequencies. So please go ahead and click on this link. I'm going to give you one or two minutes just to catch up, and a small break of 1-2 minutes so that you get this ready. Okay, so if the link worked correctly, you should see something like this. Please let me know in the chat if you're having issues with this and we can help you. In theory, you should be able to run it directly from that same link. Have a Gmail account. But if you have any issues, let us know. I think one option is also to save a copy in Google Drive, and that should allow you to make changes as well and run the different simulations. Okay, so as you will see, compared to the tutorial from this morning, this tutorial only has 2 different Jupyter Notebook cells. The first one allows you to install the required components, which in this case is Neuron and NetPyne, and just test that everything works correctly. So please go ahead and run that one. So you have to press Control-Enter or Shift-Enter. You have to be signed in because I opened it on a incognito window. So let me just do that. Oh, okay. So maybe I'll open it in a normal window. Okay, so now it should work. So once I click that, running that cell, it's going to install Neuron and NetPyne. It's set up so that it hides the output, so you don't see all the stuff that happens when you install it, but it should be running in the background. And the only other cell with code is defining the whole network model. So I did it on purpose on a single cell so that you can run the whole thing with a simple click, a simple Shift-Enter. So I'm going to go through this example just to illustrate the different components of how to define a NetPyne model. Is anyone having issues with running this tutorial online in the Google Colab? Please let us know before starting now. Okay. So the first thing that we have to do for a NetPyNE model is create this structure called NetParams. So NetParams is an object that's going to contain the whole definition of our network model, and we can create it using this line here, where it's stored in the specs module, the class NetParams, and then this allows you to start filling in each of the components of NetParams. These components are going to be the same that we were using in the GUI. So for example, for the populations, or we can start with the cells as in the GUI. You're just going to define the cell types that you want to use. In this case, we're going to have a single cell type called pyramidal. And to define a cell type in NetPyNE, what you need to do is specify the sections of that cell type and the elements inside each section. So this is a hierarchical in the same way that the GUI shows that. So we create a dictionary, an empty dictionary first. And inside the dictionary sections, we can create the soma, which is going to have a geometry and some mechanisms. For the geometry, we can specify things like the diameter, the length, the axial resistance. As you can see, all this is in a declarative format. So it's using dictionaries and lists. So that's a bit different from how we were doing it this morning in the neuron tutorial, where you had to run a procedural command to set each of these parameters. In NetPyNE instead, you're going to fill in these dictionaries, which then in turn are going to be used to generate the network model internally. So we have the geometry. Next, we can fill in the mechanisms. And in this case, we're just going to have a single Hodgkin-Huxley mechanism. So that's the HH here. And we can define the different parameters of the Hodgkin-Huxley mechanism. The sodium, maximum sodium conductance, maximum potassium conductance, GK bar, the leak conductance, and the reversal potential. Okay, so these are standard parameters. And then we tell NetPyNE that we want to store all these sections, all these properties of the cell, as a cell type called pyramidal. Okay. So NetParams, which is this whole structure containing the whole network model, inside has an attribute called cell parameters, where we define the different cell types. So now, if we...
Salvador, there's some errors piling up in the conversation. Do you want to take a quick look there?
Okay. Yes, let me do that. You know how I can see the chat when I'm sharing screen, or it's not possible?
I couldn't see it when I was presenting. There was an exception in plot raster. Matplotlib is required for plotting when the default backend matplotlib is selected. Import error, matplotlib is required for plotting.
Okay, let me try.
It's just the raster, everything else works.
Okay. So it seems like it's working here. So you have, yeah, I mean, if you load the same one and you run them in order, I believe it should work because we're all using the same exact Google Notebook. So maybe you were missing one of the steps. So if you load it from scratch and run this first cell first and then this one, it should produce this output here. I was indeed getting that error before, and I fixed it just by adding these lines here. So actually, I think if you run it again, it worked okay. It's some issue.
We don't see your screen anymore, Salva.
Oh, okay, sorry. Let me share the screen. Sure. Yes, I was saying if you run the cells in order from the Jupyter notebook that you loaded from the Google Colab, and you run this one first, I think that fixes the issue with Matplotlib. It's something to do with the packages that NetPyNE installs in the backend and interactions with the Google Colab. But yeah, but if you run them in order, this one first and then this one, it should work because we all have the same Google Colab. And you should get these 4 figures here. Any other issues in the chat?
I think we're good now. Yeah, it did eventually run for me. I don't know how or why.
Okay. So yeah, I mentioned we defined this cell type, and then we can go ahead and create these populations. So notice that the cell types is after the populations, and in this case, because it's a declarative language, it doesn't really matter the order in which you define these different components. So I can have this before, or I could move it after, and it wouldn't really make a difference. So here we are creating two populations. We put them inside this pop params attribute entry, which is also a dictionary. So we have the excitatory population, which is of cell type pyramidal, which we define here, and 20 cells. And in this case, because it's a very simple example, we're also using the pyramidal cell for the inhibitory population, and we also have 20 cells. Next, in the synaptic mechanism parameters, we create two different synapses, an excitatory and an inhibitory. They are both exponential, double exponentials with very similar parameters, time constants, except the inhibitory one shows a reversal potential of -70, making it inhibitory. The next step is the stimulation parameters. So how are we gonna drive the network? And in this case, we have a NetStim, which was also mentioned before in the chat. So this is just like an artificial spike generator. So it generates spikes at a specific rate that you provide, in this case, 50 Hertz. And you can select the noise. So what is the randomness of these spikes being generated? So once we have created this source of stimulation, we can tell NetPyNE where do we want to connect this source of stimulation, to what cells do we want to connect it. And so we say the source is background, which we just created here. And we say that the conditions of the cells that we want to connect this source of stimulation to are the ones that are in the population E, excitatory population. We want to connect them with a weight of 0.01, a delay of 5 milliseconds, and using an excitatory synapse. Okay, so this is going to drive all excitatory cells with a background stimulation of 50 Hertz and a noise of 0.5. And the next and final step to define the network is the connectivity. So in this case, we have two. These labels are wrong. They're from a previous example. So we have two connections as before, from excitatory to inhibitory cells and from inhibitory to excitatory cells. We can see here for the E to I, the conditions of the presynaptic cells is that the population is the excitatory. The conditions of the postsynaptic cells is that the population is the inhibitory. And here we're using a connectivity rule of divergence of 1. So it's connecting one excitatory cell to one inhibitory cell with a weight of 0.01, 5 millisecond delay, and excitatory synapse. And similar for the I to E connectivity rule. So finally, we set the simulation configuration options, which was another tab in the GUI as well. Here we want to run for 1 second of duration. We want to record the voltage of the soma, and we want to plot a number of plots here that we can customize. We want to plot the traces, we want to plot a raster plot, the spike histogram, and a spectrogram of the firing of the cells to see, actually, to check what oscillation frequency is the most strong in the network. And that's it. So these are the different components that we have to define declaratively for this network model. And as you will notice, the only actual command that we run here is this one, which says sim.create, simulate, and analyze. So this single command is going to create all the neuron network objects required for this model. it's going to run the simulation in parallel if you have like a parallel setup. And then it's going to run the different analysis functions that you requested. Okay. So you pass as arguments the net params, which is this object containing the definition of the model, as well as the simulation configuration. Okay, so if you go ahead and run this cell, this Jupyter Notebook cell, you will get the output below, hopefully. So it gives you a brief description of what's going on. So here it says we're creating a network of 2 cell populations. Total number of cells is 40, 300 synapses, and we run the simulation for 1 second. It generated 580 spikes. And we can have a look at the different plots. So this is the voltage trace of the soma of one of the excitatory cells. And we clearly see the spikes. This is the raster plot. And this has a peculiarity that because in this network, we want to focus on the oscillations that it's generating, we added these sync lines, synchronization lines. So wherever there is a spike, you're going to see a red vertical line going down. And this is helpful to group sets of spikes and identify the oscillations in the network. So here we see that they are very clearly grouped in subsets. And just by counting the sets of red lines, you can almost calculate the oscillation frequency of this network. So in this case, it's like 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, around 15 hertz. So we can also see that in one of the plots below. So this is the spike histogram, which is going to show a similar oscillatory pattern. And if we look at the spectrogram, we see that there is a strong peak in around 15 hertz. So the next thing we're going to do is just play around a bit with the parameters of this model and see how we can change a few parameters to obtain different oscillations. So the first thing that we want to do is just remove the inhibitory connections. And this is going to result on the removal of oscillations, because oscillations here in this case are generated through the interaction between excitatory and inhibitory connections. So if we set the probability of connection from I to E to 0, and we run the model again, by the way, the changes that I'm going to make are described here at the bottom of the Google Colab. So we're just going to play around with 3 different parameters, and you can test them at your own pace. So if we now look at the raster plot, we see that there's no clear synchrony. There are spikes all along the duration of the simulation. Again, the spike histogram is much more muddled than before. And if we look at the spectrogram, we will see that there's no clear oscillatory peak. You see these big strengths here at high frequencies, which usually means there's nothing there. Okay, so I'll give you a few seconds just to catch up with this. And so let's put back this probability of connection that we have. So we have these inhibitory connections projecting to excitatory cells. We put back 0.7. And now we're going to play with the delay, the connection delay between inhibition and excitation. So we already had it at 20 milliseconds, which is one of the changes that I wanted to make. So let's set it to a lower delay, 5 milliseconds, and see what effect that has. So we're changing the connectivity delay between I to E from 20 to 5. In the description, it says it the other way around, so I forgot to change it back. It doesn't really matter. Okay, so now we see that that has clearly changed the oscillation frequency. So if we look at the raster plot, we see that we have more of these subsets of spikes grouped together. And if we go down to the spectrogram, we see that this has increased the oscillation frequency of the network from around 15 hertz to 25, maybe 24, something like that. Okay, so by changing the time delays in the network, you can play around with the oscillation frequencies. And just as another illustration, we're going to go ahead and change the time constant of one of the synapses. So the inhibitory synapse has a fall time constant of 5 milliseconds, and we're also going to change that to 20. So this is going to provide sustained inhibition for a longer period, and that will also change the dynamics and the oscillatory period of the network. Okay, so we run the simulation, and we see that in general there are fewer spikes because we have prolonged inhibition, and the oscillation period has changed to a much lower frequency. So if we look at the spectrogram, there's no clear peak now, but we see one of the strong ones around maybe 10 hertz and also around 18 hertz or so. And we also see that it decays over time. So oscillations, the power of the oscillations decreases as you advance the simulation. So yeah, so I think that illustrates how to use code in NetPyNE just to quickly simulate these networks and play around with parameters and see the effect that they have on the dynamics. So the next thing I want to illustrate is that you can also use the Jupyter notebook that is embedded in the GUI, in the NetPyNE GUI that we were using before, to run the same kind of examples. So unless there are any questions or issues, let me maybe stop sharing, check the chat.
There was one question, Salvador. Is there a way to get a model downloaded from ModelDB into NetPyNE right now?
Into the NetPyNE GUI,
Yeah.
it's actually possible, yeah. So you can use the, let me share the screen, the upload button that we added in the menu. Okay, so I'm gonna share a screen here. And if I go here, there is in the file Workspace upload and download options. So this means that you can get to the Workspace, that is the list of files that are available to the GUI. You can upload your own files. So you can upload like Python or Hawk or even mod files. You can select multiple of them at the same time. And then those will appear when you open or import models. So if you click import from Python, you should be able to navigate and see some of the files that you uploaded inside the uploads folder. But of course, this is gonna.
That's not going to port an arbitrary neuron simulation into NetPyNE. That's really has to be done by hand.
Yes, from ModelDB, you need to do a bit of work before it's converted into NetPyNE. So you will need to import the different cell types and then extract sort of the connectivity features and stimulation parameters and implement those in NetPyNE. But for example, cell models from ModelDB, you should be able to use most of them directly and import them into your own NetPyNE network models. And in the same way, you can use this workspace to download any files that you generate from your simulation. So for example, if you generate an output simulation file, a pickle file or a JSON file, you can download it here. And this would be made much easier and much more flexible once it's connected to the open source brain and you have like a whole platform and interface to navigate with your own workspace and files. Any other questions? Okay, so just to finish off, I wanted to illustrate that you can do this kind of coding examples also using the NetPyNE GUI. So I'm gonna go ahead and click on new blank just to get a new empty one. And I'm gonna copy the code from the Google Colab. So this, just the code defining the model. We don't need any of the first lines here, the pip install, we don't need that. So we can just copy all this from matplotlib inline down to the simulate, create, simulate, analyze. Let me just set the parameters as before, set this to 5. So I'm gonna copy this code. And I'm gonna paste it on the Python console available in the NetPyNE GUI. So to open that, I go here on the left-hand side menu, click on Python, and this will pop up. So something I can do is maximize this Python window so it's easier to work with. For that, I click on the right-hand side here in the Maximize button. Okay. So again, I go to Python. Let me close this to show you again. Go to Python and then Maximize. So I see I have this line from before. So if I want, I can delete it just for clarity. To do that, I click here on the line on the left and I press DD. Twice this. DD. That clears it up. And I'm just gonna paste the whole model definition. So this is from the Python script that we just ran in the Google Colab. I'm gonna paste it here. Okay, just to show you it's the same thing. And I go ahead and run this Jupyter Notebook code. And of course, I get the same exact output of the simulation that I was seeing before, because this is just another instantiation of a Jupyter Notebook. So we get the traces, we get the raster plot with oscillations. Right now we have this dark background, but we're gonna fix that so it's possible to see more clearly the results. And we have the spectrogram here. So anybody having any issues with this? Okay. And now the interesting feature that I want to mention is that because we have this Python console embedded in the NetPyNE GUI, what we can do is transfer this model that we define using this Python code into the GUI, so that we can visualize all these components in the GUI. And to do that, we have to tell the NetPyNE GUI that this is the netparams and simconfig objects that we want to use. So I'm gonna type here the commands that we have to write for those. And I also included that in the slides. So if you go to the slides, here it explains how to open the Python console. And here are the two commands that we need to type. I'm actually gonna copy them from the slides. So this is telling the NetPyNE GUI, which is called Gepetto because Gepetto is the framework used to develop the GUI. So we copy these two lines and we paste them here at the bottom. So now we're telling the GUI that we want to use these objects that we define programmatically to populate the whole GUI. So once I run that, if I now minimize the Python console, I will see here at the top. If I move to the different components, you see that all the model elements are included and shown in the GUI. I have my pyramidal cell type with just the soma and the H8 channel that I define. I have my two populations, E and I, synaptic mechanisms, these two connectivity rules that I was playing with before. So this 0.7 probability of connection that I change in the code, I can change it directly here. Stimulation and the simulation configuration. So the good thing about the GUI is also that they is completely in sync with the backend Jupyter notebook. So for example, if I wanted to change again this probability of connection, I could go here to NetPyNE Gepetto, netparams.conparams. This rule is called I2E. And I want to change the probability. Probability. So I can just check first what is the value. It tells me it's 0.7, and you can also see it here. And I can set it to whatever value I want. So I maybe want to set it to 0 just to show the same example as before. So I can run that, and you automatically see that the probability has changed in the GUI. As you see, it's completely synchronized. I can change it back here in the GUI to 0.5. And then if I go and check my Python Jupyter notebook, I will see that it's 0.5. So this allows you to copy any script, Python script that you have with a NetPyNE model directly into the console, and then explore your model using the GUI. So with that, I can now go to create network. I can see the cells. They're very simple. They have one component on one section as only, but I can plot this connectivity. I can have a look at how the cells are connected, and I can run my simulation from the GUI and get similar results to what we were looking at before. So if I plot my raster, I will see that there's not much synchrony here, so I can plot the power spectra. Here. So we removed the inhibitory connections are there, so there is some synchrony, and we see a peak here at around 25 Hertz, more or less. So we could go back, change some parameters, and run the simulation again, and do the same exploration we were doing with code directly on the GUI. Okay, and finally, I just wanted to show that you can also run the tutorial that was shown this morning from for RxD, for example. You can run it here. So just to illustrate that it's a normal, fully functional Jupyter notebook. So I'm just gonna go ahead and copy the code for that. This is the step-by-step tutorial that you ran this morning that Robert was showing. So if I copy that into one of the cells, it has to install first this Plotly package just to be able to represent the 3D graphics. And so this is kind of a way of currently taking advantage of both advantages of the GUI being developed purely in Neuron, the new GUI that Robert was showing, as well as the NetPyNE GUI. So it's now running the model. It successfully installed the package. And we should now see one of these 3D RxD plots with the concentration of calcium, I believe, within the cytosol. Okay, so here it is. You can move it around and play around in the same way as we're doing this morning. Okay, so this concludes the coding part of the tutorial.